We're going to move on to another area of integration. So we've talked about the concept of integration. One aspect of integration that we've already talked about is the aspect of antiderivatives. So this aspect is just the reverse process of a derivative, and we use the symbol take the antiderivative or integral with the function with respect to x. We're going to move into another area of integration, which is sort of a definite integral idea. And this definite integral idea has a context to an area under a curve. So one context is that we're doing an antiderivative, where we're doing a reverse process of a derivative. And the other context of integration is we're doing an area under the curve of a function from x equals a to x equals b with respect to x. So we're moving into the idea of a definite integral, and this forms our outcome I2, and the process of taking an antiderivative forms our outcome I1. Now, in order to kind of understand how this developed, we want to pay attention to finding areas under the curve. So let's do some examples where we're finding areas under the curve. We've already know how to do this for some functions, but as the functions get more complicated, now we have to start introducing integration. So let's say I have a function f of x equals 5, just a constant function. I'm interested in finding the area under the curve from x equals minus 1 to x equals 4. So 1, 2, 3, 4. So I'm interested in this area. Now, one idea you can look here is that I don't actually need integration to do this because these are just simple shapes. So today we're going to focus on the simple shapes. Okay, in this case I have sort of a rectangle happening. So the area under the curve is going to be equal to the length times the width. And the length of my rectangle is 1, 2, 3, 4, 5 units long. The width of my rectangle is 1, 2, 3, 4, 5 units long. I should call it a square, not a rectangle, because obviously the length and the width are the same. And this gives me an area of 25 units squared. Now I can use a definite integral to represent this area. So I can say the definite integral from minus 1 to 4 of my function. And I know that this representation of these symbols that I wrote refer to area under the curve, because that's what we're trying to say. And this is equal to 25 units squared. So when there's simple shapes involved, we're just finding the area of those simple shapes. Let's look at another example. I give you a function, f of x equals x plus 1. I'm interested in the area under the curve from 0 to 6, so 1, 2, 3, 4, 5, 6. So the shape that's being formed is a trapezoid. So this trapezoid, when we want to find the area of it, I'm going to call this distance f of a, the height of that. I'm going to call this distance f of b. So the formula for the area of a trapezoid is we take the height of the trapezoid, which I'm going to call sort of like the base in this case, and then we're going to do the two differing heights. So this is a height that's different than this height. So we do f of b plus f of a, and we divide that by 2. Okay, so I'm going to represent this through an integral. I'm interested in the area under the curve from 0 to 6 of my function dx. We can always go ahead and put that function in for f of x. So this is just x plus 1 dx. And then I know in this case my area is based on a trapezoid, and I just do the area of this trapezoid. So I do my height, which is 1, 2, 3, 4, 5, 6 units long, which is sort of the 0 to 6. And then my f of b, this height, would be 7 units because it's the x value 6 being subbed into the function. I take my other height, which is 0 being subbed into the function, so that's 1, and I divide it by 2. So 6 times 4, 8 divided by 2 is 4, and 6 times 4 is 24 units squared. Now there is a trick on your calculator. You can use the button Math, number 9, which is function integration, and you just kind of type in the function, put in the dx, put the numbers on the limits, and it should confirm this answer for you. We're not going to be using the calculator in the course, but at least I just wanted to introduce it so as you're doing work at home, you can kind of check your answers as you're going along, just sort of as a check. But again, in our course, we don't really allow you to use a calculator, to try to think through this stuff. So, and we're just going to keep continuing finding areas under curves using simple shapes and then representing this area using an integral. So I'm interested in finding the area from -3 to 6 of my function. My function is an absolute value, dx, with respect to x. So I'm going to go from -3 to 6, 1, 2, 3, 4, 5, 6. And this time I'm looking at this area under the curve. Now what I can do with this area is I can kind of break it up into 3 sections. I can call this area 1, area 2, area 3, and then my total area under the curve is going to be A1 plus A2 plus A3. I have 2 triangles, so the first triangle is 1/2. The base of the triangle is 1, 2, 3, 4, 5 units long, times my height, which is 1, 2, 3, 4, 5 units tall, plus my area 2 is also a triangle, 1/2. The base is 1, 2, 3, 4 units long, times my height, which is 1, 2, 3, 4 units long, plus my A3 is a rectangle, so it's going to be base times height or length times width. So my height is 2 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 2 times 9. And then I just kind of clearly work this out on my calculator, which I'm not going to do for you right now, but you just work that out. And then the answer would be this many units squared. Okay. Now we get a semicircle. Now we know that the area of a circle is, the equation of a circle is x minus x naught squared plus y minus y naught squared equals r squared. Now if you rearrange this equation for y, you get sort of y equals plus or minus, and then you get an expression here. Now I want you to understand that the positive version represents the top half. So that's why when I rearrange, this is the positive version, is the top half. The negative version refers to the bottom half of the circle. So sometimes they'll give you a top half and sometimes they'll give you a bottom half. We're interested in the area under the curve for the whole circle, just the top half of it. So I'm going to write that using an integral. So the integral from -6 to 6 of the square root of 36 minus x squared dx. Now this function here is not actually one that you're going to actually learn how to integrate in high school. This is going to be in your second calculus course. If you do this, you'll learn how to do that in Calc 2. So it is important to know that if I was going to ask you this question on an assessment, you can't actually find this area, you can't actually find this integral. You would have to do it as an area under the curve, which is quite simple. It's 1/2, because we're a half a circle. Pi r squared is the formula for the area of the circle, so my radius is 6 squared. So 36 divided by 2, this gives me 18 pi units squared. So like it could be centimeters, it could be meters, depending on the context of what we were working with. Okay, now pretty much we are dealing with an area problem. Okay, just like before we kind of dealt with the tangent line problem, you need to know what is an area problem. So the area problem is that I have a function that doesn't have such a simple shape. So I give you this function, f of x, has a lot of curves to it, and I'm interested in finding the area from x equals a to x equals b, and we're interested in the area that lies above the x-axis. Okay, so this region S, described by inequalities here, is exactly just an inequality to describe this region S, which I'm interested in finding the area of. Now in statistics, there's kind of reasons for why you would want to find that area under the curve, because that would actually represent probabilities. So it is important to know areas under curves, and so what we do is we are interested in finding this exact area. Okay, so in order to develop these ideas, we're interested in these exact area. We can use simple shapes to do it, which is kind of what those above examples were illustrating. And then we're going to say, okay, well, what if we want to move away from simple shapes and we have a funky curve? Then we're going to get into some approximation methods. And then these approximation methods will help us develop the ideas for how we would actually do this in reality. So we are going to learn 4 approximation methods. One of them is that we're going to form rectangles, and we're going to break up our interval. So let's say this is our interval A to B. We're going to break up this interval into some regions. So let's just say in this case, this many. And the question would tell you how many to break it up. And then we're going to approximate the area by using the left point and creating rectangles. Now the height of this rectangle would be just the y-coordinate at the left endpoint, but this is called your left endpoint method, or your left Riemann sum. I could use an approximation by using the middle of each rectangle to form the height of the rectangle. So if I look at the middle of each interval, in this case I only broke it up into 3 subintervals, but the height of that rectangle is based on the midpoint. So that would be called our midpoint approximation. We could break it up into rectangles. We can use more rectangles or less rectangles. So this is my region A to B, and I've broken it up into rectangles. I could use the approximation by using the right endpoint and forming the rectangle at each right endpoint. And that could be my approximation. That's called our right endpoint approximation. And those are rectangles. Now you can hopefully recognize here that the larger the rectangle, the less accurate potentially the value can be, because I've extra counted this one. I haven't counted that area when I needed to. This is all extra, this is all extra, and then there's some here that I haven't counted. So kind of the idea is that the more rectangles you include, the more exact that the answer is going to be. Now the last approximation we're going to do is a trapezoid. So what we do is we break up our interval, and then what we do is go to the height of each rectangle, and then we just use a trapezoid, or a line joining those 2 points, to make the trapezoid at each point. So I take this endpoint, make a line between them. That forms sort of the trapezoid of that section. So let's go through an example. We're going to estimate the area under the parabola of y equals x squared from 0 to 1. We want to use 4 rectangles. So we're going to go through the first method, which is using left endpoints. Now I can't use simple shapes because I don't have a simple shape that gives me that area of this curve. So we're going to use 4 rectangles. So I'm going to go 1 minus 0, so that total distance between A and B, so this is my A, this is my B. I find the total distance between A and B by subtracting the 2, and then I break it up into however many rectangles I want. So in this case I want 4 rectangles, so each rectangle length is going to be 1/4 unit along. So I start at 0, I go 1/4 unit along, that's my first kind of increment. I go another 1/4 unit, 1/4 unit, and then by the time I hit the last one, I've formed 4 rectangles. Now what we do is, if we're using the left endpoint method, then what we're doing is we're taking the left point of each rectangle and forming the rectangle. So there's the first one. There is no rectangle there. I take the left endpoint, that forms the height of the rectangle. Okay, I take the right endpoint, that forms the height of the rectangle, that third one, and I take the left endpoint, and that forms the height of my last rectangle. So now what I'm going to do is to actually approximate that area under the curve. So the integral from 0 to 1 of x squared dx. Again, we're using this definite integral representation to represent the area under the curve. All this is going to be is the 4 rectangles added up. Rectangle 1 plus rectangle 2 plus rectangle 3 plus rectangle 4. Now this is not going to be exact. This is going to be approximate. Okay, so I take my base, which is 1/4, times my height, which there is no height there, plus 1/4. The height of this rectangle would be based on the height of this value of the function, which is just the function at 1/4. So this would be 1/4 squared plus 1/4 is the base of the third rectangle. The height is dependent on the left endpoint being subbed into your function. And then the last rectangle has a width of 1/4 and a height of the last end or the left endpoint being subbed into the function. So you recognize that these ones are just the function at the left endpoint. So you see we start at 0, we go 1/4, 1/2, 3/4, but we kind of ignore the last endpoint because it's a right endpoint. I kind of just plunk this all into a calculator or a computer software program or something like that, and this would be that many units squared, and that would be an approximation. Now in this case, I've broken up that area into 4 rectangles. It's not a great approximation. Is my answer going to be bigger or smaller than the actual area? Well, there's all this white space I haven't counted, so we're going to say that this is an under approximation to the actual area under the curve. The value I'm getting is smaller than what I would actually use, like the actual area under the curve. Now method 2, we're going to use right endpoints. So I have my interval 0 to 1. I take the difference and divide it into however many rectangles I want. That tells me the width of each rectangle is 1/4. So I start at my left endpoint 0, add 1/4, add 1/4, add 1/4, add 1/4 till I'm at the end point B. So now my area, the area under the curve from 0 to 1 of x squared dx is going to be approximated by, you can use the squigglies here if you want, or you can use the equals with the dot on top as an approximation. So I'm going to do my width of the rectangle times the height, and the height of that rectangle is dependent on the right endpoint this time. So it's going to be the function value at 1/4, plus I'm going to do 1/4 times the function at 1/2, plus I'm going to do 1/4 plus the function at the right endpoint. The height of this rectangle would be the y coordinate at 3/4, plus the 1/4 times the height of the last one, which is going to be the right endpoint being subbed into the function. Okay, so this is going to be equal to 1/4. My y value is 1/4 squared, plus 1/4. My y value is 1/2 squared, 1/4. My y value is 3/4 squared, plus 1/4, 1 squared. And then you just work that out. It'll be that many units squared. In reality, we would probably put this into a computer software program and do more rectangles so you can start to see what's happening. And now you can see that all this blue is extra area that we counted, but it's not actually representing area under the curve. So this answer is going to be an overestimate of the real answer. Now again, as you take more rectangles, you will get an answer where these extra spaces, all this stuff extra in blue, gets minimized. Okay, so the more rectangles you take, the more accurate your answer will start to be. Method 3, now in this example, they've given us less information and we have to draw some rectangles in there. We're going to do midpoints this time. So here's my interval, 0 to 1. You can see that this is just a screenshot from Desmos. So we let me just kind of highlight our x-axis here. We have 0 to 1. We still have 4 rectangles, so this is going to be 1/4, 1/2, 3/4, and then 1. And then what I'm going to do is I'm going to use the midpoint of each of these to find the height of the rectangle. So the midpoint between 0 and 1/4 is 1/2 of 1/4, which is 1/8. Then we get 2/8. This would be 3/8, 4/8, 5/8, 6/8, 7/8. So those values in pink are the midpoint of each rectangle. So I take the midpoint, I form the rectangle. There's the first one. I take the midpoint, I form the rectangle. I take the midpoint, I form the rectangle, and I take the midpoint and I form the rectangle. So you can see that sometimes this midpoint may or may not be an over or under approximation. This looks like there's some overage amount and some underage amount. It's kind of actually hard to tell if there's more over or more under, but usually it'll be really clear if I give you an example whether it's an over or under estimate. So this would be the length of the rectangle times the function value at the midpoint this time, plus the length of the rectangle. The function at the midpoint will be the height of the rectangle. These expressions just represent the area of each of those 4 rectangles. 1/4 times the function value at 5/8 plus 1/4 the function value at 7/8. Okay, we take our function value, sub it in. So my function is x squared, so this would be 1/8 squared. 1/4 times 3/8 squared plus 1/4 times 5/8 squared plus 1/4 times 7/8 squared. And again, you would just put this into your calculator and that would be my answer for the approximation for the area under the curve from 0 to 1 of x squared dx. So these are just approximations. Again, the more rectangles you take, the closer you're going to get to the real answer. Okay, method 4 is a trapezoid. So we've already talked about sort of the formula for a trapezoid. So I'm going to take this, I'm going to rotate it sort of by 90 degrees, and I'm going to drop this bottom section because my trapezoid will not have that in there. So we sort of get their trapezoid in a format like this. So this is the left end point, this is the right end point, and I kind of just connect the left and right end point with a line. This is sort of the height that they're referring to. This distance is A, this distance is B. In our case, they're like function values. And then the formula for the area of a trapezoid is just given by A plus B over 2 divided by 8 or times H. So now we're going to estimate the area under the curve using trapezoids. So there's 0, there's 1/4. I form a kind of a diagonal between the two. There's 1/4, there's 1/2. I form a trapezoid. There's 1/2, there's 3/4. I form a trapezoid. There's 3/4 and 1, form a line, and there's the trapezoid. So I'm going to do those 4 trapezoids. So the integral from 0 to 1 of x squared dx is approximately equal to, so the length, so the h. Now you'll notice that this h is going to show up in each trapezoid. So what I'm going to do is that h is going to be 1/4, and I'm going to factor it out. So now I just need to do this part for each trapezoid. So I'm going to do the function, the function value at the left plus the function value at the right, divide by 2, that will form my first trapezoid, plus I will do the function value at 1/4 plus the function value at 1/2, divide by 2, plus the function value at 1/2 and 3/4, that will form the third trapezoid, plus the function value at 3/4, plus the function value at the last one over 2. So you're going to notice you're going to do the y of the left, y of the right, divide by 2. Y of the left, y of the right, divide by 2, and so forth until all your rectangles are covered. You plunk this all in your calculator carefully, and this will be units squared. So again, function at 0 would be 0 squared. Function at 1/4 would be 1/4 squared, because my function is x squared. This will be 1/4 squared, 1/2 squared. 1/2 squared, 3/4 squared. 3/4 squared, and 1 squared, and then you just plunk all of that in. Okay, now there's a student example 1 here. So what I want you to do is work through this one. Work through this. It's pretty straightforward, except now my a value is going to be 0. My b value is going to be 9. My function is going to be root x. How many rectangles do I want? 6. So my n value is 6. Sketch the graph of the rectangles. Approximate each using the 4 methods. Decide if it's an over or under approximate. So what you can do is you can do the value from 0 to 9 of root x dx. Now, at the moment, I have not shown you how to evaluate this. We don't know how to evaluate this. So for now, if we want the exact area, the exact value, we would just do on our calculator, math, number 9, which is function integral. You'll see when you put it in exactly what to type in. And it will kind of give you a blank box here, a blank box here. It'll give you a bracket with a blank box here, and then it'll kind of have a dx on the outside, and you just carefully type everything in, and that will give you the exact area. Then you're going to do your left approximation, your right approximation, your midpoint approximation, and your trapezoidal approximation. You can compare these answers to the answer, the actual answer here, and decide is the answer bigger or smaller than what it should be. Depending on the curve you get, sometimes if the curve is always increasing, you might get an over approximation in one method but an under in the other. So you're going to carefully work through that. If you put this example into the Dropbox, into an assignment Dropbox under approximation methods or something labeled like that, I will go through it and make sure you've done it correctly. So you should try this example out. Okay? Now what happens if we increase the number of rectangles used? So this is kind of where we're heading next. So now in these examples, I've used 8 rectangles. You can calculate this answer if you wish, but again, in reality, this is not really great to do by hand. We would have computer programs to do this for us. Now, when I do 10 rectangles and use a right approximation, I get 0.385. And when I do 10 rectangles and then use a left approximation, I get 0.285. Now you can see that the rectangles on the top here, there's extra rectangle on over top of the function, so these are upper sums. These are bigger than the real answer. And then these ones are lower sums because they're lower than the real answer. So these are over approximations. These are over approximations when you do the right endpoints, and these are under approximations when you do the left endpoint. Whoops, I can't spell approximation today. Under approximations. Again, in this case, the reason why they're being like that is because of the function being increasing. If the function were decreasing, this would probably reverse. But you can see, as the number of rectangles I take goes to 50, these answers are starting to get closer and closer to one another. So we keep going. Computer programs can do this for you. When we get to 1,000 rectangles, again, these numbers are getting really close. So again, what we want to kind of do when we're doing this is we want to take n approaching infinity. So n represents the number of rectangles. we want the number of rectangles to become infinite. We want so many rectangles that essentially we're getting the exact area under the curve. Now when I do this and I look at these two values, you can start to see that the decimal places are lining up at 0.33, and then there's a whole bunch of differences in there. But as the number of rectangles increase, and you were to take the limit of the number of rectangles increasing of that sum, you're getting 1/3. Okay, that's sort of like a limit. So the area problem, we have a definition now, okay? So the area of the region S from way before when we defined the area problem lies under the graph of this continuous function, and this gives you the sum of approximating rectangles. When I'm using an R, I'm using the right endpoints. So I take the function value at the right endpoint times the height, plus the function value at the right endpoint times the height. Now if my rectangles are x0, x1, x2, all the way to xn, the right of each endpoint will start at x1 and go all the way to xn. Whereas the left endpoints will start at the very left, which is x0, but it will skip the last one because the last one is a right endpoint. So this is your right Riemann sum. This is your left Riemann sum, is what we call them. Using left endpoints when you use the L symbol, or using right endpoints when you use the R symbol. Okay. Okay, so these are just areas. We will continue this lesson.